Good morning, everybody. It's been a while since we've met in the studio. If you could give some green check marks in chat, and if you had any questions from last day's material, I know I left you guys with some work to do and the simulation, and I said I'd answer any questions you might have had today. So if anything you wanted me to go through, we could. And one other thing is that we were scheduled from 9 till 10:20 or whatever. Turns out I don't have class at KSS, so I might stay a couple minutes late, if that's all right with everyone, just to get through all of the stuff we need to get through today. So there you go. A couple from the assignment, a couple from the learning guide, page 6, number 11, 12. I assume that's off the learning guide there, Taylor. And is there anything else that came up? I'll jump over to the learning guide and then we'll go from there. Page 6, 4, 5, 6. All right. Page 6, number 11 and 12. Of course, I didn't bring my calculator, so you guys are going to have to help me out here. Half-life isotope of sodium is 15 hours. Initial sample contains 1,000 grams of sodium-24. What mass of sodium-24 will be left after 3 days and 12 hours? Show your work. All right, we can definitely do that. Ava, what questions did you have out of the learning guide, just so we can make sure we get those as well, and see how we do here. 13 and 14 on page 6. So I'm doing all of the half-life questions. All right, that's okay. All right, so number 11 here says the half-life of sodium is 15 hours. So we need to figure out how many half-lives are going to occur in the amount of time that we're given. That's kind of the first step. Now, sometimes doing these half-life questions, it makes it really easy if you put everything in a table. And it doesn't really matter what your table looks like, but you can start with something like this. So you could have number of half-lives, and then you can have something like time, and then amount. And you can just kind of go through it like this. Just want to make sure I have enough room here. All right, so if I have 0 half-lives, I have 0 time passed, and I have 1,000 grams or a kilogram. And then I just kind of keep going. After 1 half-life, I have 15 hours have passed, and I have 500 grams left. And I just keep plugging away until I end up with the amount that I'm asked to find. So the important thing about the question here is to read it very carefully. It says initial sample contains 1,000 grams sodium-24, and then the question asks for what mass of sodium-24 will be left. You'll notice some questions will ask about the daughter material, so the isotope that's actually created. So it makes the question kind of backwards. So if you've lost 75% of your original isotope, your parent, then you know how much of the daughter has been produced. So you can the questions can vary just depending on what they're asked to do. So I don't know, let's go through this a couple more times and see where we end up. So 2 half-lives is 30 hours, and I'm down to 250 grams. And 3 half-lives is 45 hours, and I'm down to 125 grams. 4 half-lives, not 50, 60 hours. And what am I down? 1262.5 grams. And I can just plug away like that. Now, the question asks for 3 days and 12 hours. So 3 days is 24 plus 24 plus 24, and then another 12. So 24, 48, 60, 72, 84 hours. Did I get that right? 4, 4, 4 is 12, 13, 14, 2, 4, 6, 7, 8. Yeah. So we're looking for 84 hours. Thank you, Ava. So let's see if I can fit another one. 5 is 75 hours. And what are we down to? 31.25. And can I jam one more in here? I can. 60, 80, that gives me 90. And I have 31.25, so 15.5 grams. So if I'm at 84 hours, I'm going to be somewhere between 31 and 15. And you can just go from there. 3 days, 12 hours. Just trying to, generally speaking, when you have these types of questions, there'll always be ones that kind of work out to the exact half-life. So I'm reading this 84 hours and I'm wondering kind of why it's 84. Why isn't it 75 or 90? So generally speaking, this number, the number of hours, will work out to a perfect number of half-lives. Is there a way to work out the exact mass? Yes, there is. And I'm drawing a blank on the equation because there are ones that we use for Physics 11 and we don't use for Science 10. So for this, I think just estimating it'll be fine. I'll see what I can do. I'll find the equation for you guys before the end of class, and we'll see if that works out any better. But essentially using the equation is just going to make your life a lot more difficult than it needs to be. These questions aren't generally this difficult. So there you go. Half-life isotope sulfur 35, it's 87 days, 300 grams. How much will be left after 1 year? You'll need to calculate the number of half-lives, then pass to one decimal place, then use the graph on page 2. So it's asking us to do the same sort of thing and then refer to, of course there is no graph on page 2. You can use one of the charts from up above. Once you figure out the half-life, half-life and percentage charts that we've drawn a few of, you can use one of those to figure it out as well. I'll leave you with that. Let's look at 13 and 14. You can do number 12 the same way with the chart that I showed you. 13, 14. Fossils analyzed, determine percentage of original carbon, 14 remaining is 25. How old is the fossil? So let's do the same chart as we did up above. Half-life, time, and this one we're dealing with percentage. So 0 half-life, 0 time, I have 100%. 1 half-life, 5,730 years. I have 50%, 2 half-lives, 11,460 years, I'm at 25%. So if I wanted to know how old it was, I've gone through 2 half-lives. Each half-life's 5,730 years. And away you go. Does that help you, Ava? 12-gram sample carbon-11 is left in container for 60 minutes. The mass of carbon-11 is now 1.5 grams. What is the half-life of carbon-11? This is just the same sort of process with the table. So you have half-life, time, and in this case, you're starting with a mass in grams. So 0 half-life, 0 time, I started with 12. 1 half-life, I don't know how much time's passed, but I know I'm going to do a half-life, so this is going to be down to 6. 2 half-lives, still don't know time, down to 3. 3 half-lives, still don't know how much time, but I'm down to 1.5. All right, so if I had 3 half-lives occur, and I know that it's in the container for 60 minutes, you could probably figure out a way to go from there. So we know that this is 60 minutes down here. So you have a couple blanks, I guess, to fill in, maybe some thinking to do, and you can kind of work your way backwards to figure out how much time it's going to take to get to 1 half-life. And if you have the time at 1 half-life, you know the half-life of that sample. So that was that. Somebody else had a question about the assignment. Did you want to throw that into chat and I can go and look at it, or maybe we can do it after, or if there's anything else from the learning guide. Just give you guys a second. This is see a couple of you are typing, so I'll just give you a second to get your message in there, and then we'll look at something else, or we will move on to today's material. Half-life of an unknown element, and then 6 and 7 at the end. This is from the assignment, I'm assuming, Ava. Is that right? Okay. I will just jump into here. I still haven't moved that assignment up. I should probably get that done. All right, so this is talking about the simulation that we went through last day, and half-life of an unknown element. Let's see if I can find where that is. About that unknown element. How would you determine the half-life of this unknown element? Write up a little plan here. Estimate the half-life of the element. All right, so if I recall correctly, when you run the simulation, you can look at the half-life. It doesn't necessarily give you amount of time, but it gives you a little chart where the atoms are decaying, and then it gives you a red line, I believe, where exactly half have decayed. So let's see if I can't run this. All right, so where is the unknown element? It's not the one I want. Uranium, it's not the one I want. I have to Find the right section, I suppose. Carbon-14 measured 5,730 years. How many blah, blah, blah. Okay, so if I add a bunch of this unknown element, I think that's the one there, I have got it. So you can see you can drag this guy around and you can move it to where you want. So if I watch the pie chart in the top corner here, the brown section is the original element, and then the green section is the daughter that's produced. So what I want to do is I'm going to play this, and then I'm going to just pause it just a little bit before half, and then just take a couple steps until I get half. So that's really close to half, 50 and 49. So that turns out to be right there. So that's a way I can find where the half-life or the half point is. So I can just reset it and see if it works a few times. I'll just pause it a little bit right there, and then just take a couple steps. And then now it's over here. That was pretty close again. So I'm just keeping an eye on the pie chart when I have 50%. So it's going to be somewhere in here. It's a little bit different each time just because of when the things decide to decay. But you can just go from there and figure out an estimate of where the halfway point of that decay is. So hopefully that helps you out there. And then I believe you asked a couple questions about the last. And then 6 and 7 at the end. So let's go down to the bottom. Make a small sketch of what a decay curve may look like for an unknown element. And you happen upon an antique store. Clerk claims belt that was once worn by Alexander the Great. Your radiocarbon date and find the percentage of carbon to be 75% remaining. Could the belt be genuine? How did you arrive at your answer? So I guess for number 6, all decay curves are going to look the same. They're all that same general sloping where they start really steep, you get half, and then you go from there. So any decay curve we've drawn in the notes or any one you've seen, they all look identical. So if you just sketch something like that, that would be fine. With the unknown element, you had your half-life at about just under 4 seconds or around 4 seconds. So you have 100% of your sample, then you should have 4 seconds pass, then you should have 50% left. Then you should have another 4 seconds pass, you'd be down to 25%, another 4 seconds, and you can just kind of draw it like that. And then this last question, find the percentage of carbon to be 75%. So that means you haven't even gone through one half-life yet. You're about halfway to a half-life. If you had 50% remaining, you would be exactly one half-life. But because you have 75% remaining, you're at about halfway between where you started and a half-life. Now we do know the half-life of carbon-14, and the half-life of carbon-14 is 5,730 years. So if I have 75% of it remaining, that means I'm about halfway through a half-life. That makes sense. So that should be around, what's half of 5,700? About, 2,350 years-ish. So use your judgment to say if it could be genuine or not. How do you sketch it on Word? That's a good question. I guess you could draw a shape, first of all. Can you get like a right angle? Yeah, let's do that. I could draw just a line down and then a line over. And then drawing, I guess you can't freehand draw in Word, can you? Is there any like, you can do shapes. What you might be able to do is this what I'm looking for? There you go, that was it. So if you go into the insert and then shapes, there's a squiggly line here, which should let you draw a nice decay curve like that. So there you go, that's how you can draw in Word. Or you could go and just find an image of a decay curve, and then you could just take a screen capture of it using like the snipping tool or something, and then put it into your document. Those would both be good ways to do it. Hopefully that clarifies some of that. Are there any further questions before we mosey on into today's material? I will maybe see if I can find some more decay questions, half-life type questions, because they are a little bit tricky, and maybe give you guys a few more of those for practice, because I think the 4 that are in the learning guide maybe just kind of scratch the surface. All right, I don't see any more questions, so we will move on to today's material. This is one of my favorite sections of Science 10, and I think because I have spent a lot of time studying physics, I enjoy this stuff a lot. And I think it's just really interesting, and students generally find it kind of interesting because you've seen some of this stuff before in your life, and it's kind of exciting stuff. It's kind of scary stuff, but it's kind of exciting stuff. So today we're going to talk about the differences between fission and fusion, and what they are, how we can use them, and sort of what they're used for, I guess. So the important sort of thing here is to draw a distinction between fission and fusion. They kind of sound the same, but they're really different things. And the really easy way to remember it is fusion. You guys know if you fuse something together, or if you go out for dinner and you're eating fusion cuisine, it's taking 2 different types of foods. So you could have like Indian Thai fusion, and they'd a little bit of Thai food, a little Indian food, and kind of mix it together and make it. Fusing something is joining things together. So fusion is a word you're familiar with. Joining things together. Fission is probably something you're not as familiar with, and that's breaking something apart. So those are the kind of big ideas. We're going to talk a little bit about power plants, and in Canada, especially on the East Coast, they have nuclear power there, and we don't have any in the West Coast for reasons we'll talk about in a second. But we have something called a CANDU reactor, and this is a picture of one. And CANDU reactors are sort of Canadian technology that's, we set these reactors up all over the world. And they're known as some of the safest nuclear reactors that exist. So we'll take a little bit of a closer look at the inside of a nuclear reactor and see how power is actually generated. So first thing we're going to talk about is fission. So if you have a really heavy nucleus, and you take that heavy nucleus and you split it into 2 or more smaller nuclei, you can end up with a large amount of energy produced. Now, the key here is that if you have something like an oxygen atom, oxygen's relatively stable. It has 8 protons, 8 neutrons. It's kind of small compared to something like uranium, which is 92 protons and 235 for a mass. So a lot of elements aren't radioactive, and they don't want to break apart. They're really stable, they're really happy. But when you get things that are really big, when you get up to like uranium, 92 protons and larger, they become really unstable because there's so many protons in the nucleus, and they're trying to push each other apart. Remember, those positive charges want to repel one another, and they're unstable. So if we add something to them, if we can hit them with something really hard, they'll break apart into two things, and then a bunch of energy will be released. So this is kind of the idea of fission. So nuclear reactions are ones we've already looked at, the alpha, beta, gamma decay type questions you guys did in 7.1. It's the same idea again here. When we have a nuclear equation, the protons and neutrons on either side of the equation or the arrow have to add up, so they have to be equal. And we end up changing the actual elements, so the elements get changed from one to the other. When we dealt with chemical equations, when we were balancing and doing things like that, we didn't have to worry about new elements being created. We started with carbon, we ended with carbon. That was the whole basis for balancing chemical equations, was you started with something, then you had to finish with it. But now that we're doing nuclear equations, you can start with uranium and you can end with krypton and barium. It's just kind of like, it doesn't really, make sense if you can start with one element and you end up with something else. But that's what's sort of special about nuclear equations. And we have the most famous physics equation ever, E equals mc squared. Einstein obviously came up with this. And do we know what those letters mean? Does anybody know what E equals mc squared means? And what we can use it to calculate? This is probably the first time in your lives where you're actually able to kind of talk about and understand E equals mc squared in the context of something where it actually makes sense, not just, oh, E equals mc squared is just a fancy physics equation. So what is the E? Alex says energy times mass. That doesn't make sense. You're on the right track though. You've seen it so much. Yeah, it's kind of one of these things that's it's in pop culture. Like everyone knows E equals mc squared. But what does it mean? What is the E? E is energy. I'll give you that one. M. What is the M? What does M usually mean in an equation? You guys have done a little bit of density stuff in grade 8 or 9, I believe. And then C is probably the letter you've never really talked about. Yeah, so E is energy and it's measured in joules. M is mass, measured in kilograms. And then C. Does anybody know what C is? C is a constant. It doesn't change. It's actually the speed of light in a vacuum, which is kind of a weird sort of thing to talk about. But light can speed up and slow down depending on what it's traveling through. So we say the speed of light in a vacuum because if you take everything away, and like space is a really good vacuum, it's just how fast light travels. So E equals mc squared. It turns out light travels really fast. And if we take, in these nuclear equations that we're going to deal with, when atoms break apart, or even when they fuse together, we talk about fusion, a little bit of mass gets converted to energy. And some amazing stuff can happen as a result. So, it's 9:30. I wanted to watch this, but then I wasn't going to, but I think I do want to watch it. So I'm going to, if I can find it. We watched A is for Atom, or I asked you guys to watch the first half of A is for Atom. This second part is about 7 minutes long. I might cut it off a little bit early just to save time, but again, this is the 1950s, so this is when we were just figuring out how to do this sort of stuff, and they produced this video. So I'm going to supersize this, see if I can get some sound going, and we'll just watch maybe 5 minutes or so of the second part of A is for Atom, and then we'll talk about some of the ideas that came up in the video, because it does a great job of kind of lining up with what we need to talk about in Science 10.
Mass and energy are really the same. But we spoke of a double miracle. To understand the second one, let's slow down that fission 1 million or so times. A single particle starts the reaction, splitting the uranium atom. Here now is the release of energy as heat and blast. Here are powerful rays being given off, similar to X-rays. But here are free neutrons driven out with tremendous speed. And provided there is sufficient U-235 present, what science calls a critical mass, those neutrons bombard other uranium atoms, causing them to split and split still others. The result? A chain reaction. Over 1,000,000,000,000,000 atoms exploding within 2 seconds. And the force? It would take Yankee Stadium full of dynamite to equal the energy released in the complete fission of an amount of U-235 the size of a baseball. With this discovery, at the time the free world faced a war for survival, it was little wonder the first thought was a weapon. But how to obtain enough material for even a single bomb? Only a small fraction of natural uranium is the U-235 isotope, which will fission in a chain reaction. And to separate enough U-235 quickly enough seemed all but impossible. But the impossible became reality as industry, labor, science, and the military combined their efforts to build Oak Ridge, where enough U-235 was separated to build the first atomic bomb. At Hanford, Washington, another impossible project proved possible when a huge plant was built for the mass production of the artificial element plutonium. This process involves what may be called the furnace of atomic energy, the reactor pile. Here is a structure or pile of graphite blocks. In the reactor are placed rods of natural uranium containing both U-235 and U-238. As U-235 begins to fission, the graphite slows down the free neutrons, and some of them hit other U-235 atoms, keeping the chain reaction going. But others of those slowed down neutrons hit U-238 atoms, and here's what happens. Remember, we said that U-238 wouldn't support a chain reaction. However, it will capture neutrons from U-235 fission and start a process which converts the U-238 first to neptunium, then to plutonium. And plutonium will fission in chain reaction. Thus, the reactor itself is a source of atomic fuel. Besides producing plutonium, the nuclear reactor makes possible two very important peacetime uses of atomic energy. Remember that the chain reaction process in the reactor creates tremendous heat, which scientists have learned how to control. Thus, a reactor may be substituted in many industrial applications where heat is now provided by coal or petroleum. But such uses in the foreseeable future are limited. For one thing, a reactor pile must be shielded to protect the workers around it from dangerous radiation, and this shielding adds tremendous weight. However, an atomic energy power plant has already proved feasible. The future supplying of electric power to entire cities is far from impossible, while nuclear power in locomotives, submarines, ships, and even very large airplanes may all but revolutionize future transportation on land, sea, and air.
All right. So obviously that was in 1952 or 53 when it was produced, and they didn't really know what the possibilities were for using nuclear energy, so they speculated that they could use it in things like trains and planes. Did it happen? Not in planes yet because of sort of weight restrictions and things like that, but we do have nuclear-powered submarines that some governments have, and some big ships like aircraft carriers and whatnot are nuclear-powered as well. So, you know, they had to speculate, they didn't know, and they thought, hey, maybe we could power whole cities with this stuff, and we do. And it's pretty cool to think that we can do that. So we're going to keep this idea E equals mc squared in the back of our heads for a second, but basically the idea is a little bit of mass gets converted to energy. And like you and me are made of mass, everything around us is made of mass. If we could harness just a small fraction of the energy converting our mass, or the mass of some uranium, directly into energy, the amount of energy produced is absolutely incredible. And we'll look at that here in a second. So this stuff's really cool and interesting and kind of different. But the only parts that you really get tested on or really come up is these nuclear equations. So just like when you were dealing with the alpha, beta, gamma decay, these nuclear equations are ones that you're going to have to be able to do. So these are an example or two examples of a nuclear equation. You can be given like an image like this one up here. This is a new feature that I have now, got a laser pointer. So the equation is here. And you can see that you have an alpha particle, and it gets smashed into this nitrogen atom. So you're adding these two things together. This is your reactants, and then you have your arrow, and then your products over here. So if you can take an alpha particle, smash it into nitrogen, what can happen is you can produce oxygen, and then you end up with a proton as well. So that's kind of what it looks like in terms of a picture. And then down here you have the same equations, but just in terms of the actual things that are taking part. So alpha particle or a helium nucleus, same thing. You have nitrogen, you produce oxygen and a proton. So these are the symbols you don't need to know because they're actually on your formula sheet. But the idea with nuclear equations is that the left side has to equal the right side. And you can end up with all these things like a proton or a hydrogen nucleus. These are the same things. You can have a neutron, which is 1, 0, N, helium nucleus or an alpha particle, an electron or a beta particle. These are all the same things. And they are found on your data booklet. I'm looking for. So this is the very last page of your data booklet. This is page 12. And you can see in the middle here you have all your radioactive symbols. So it doesn't tell you what they are. Alpha particle helium, beta electron, you have a gamma ray, a neutron, a proton, and hydrogen. So these are the things that are going to make up these sort of decay nuclear type equations. They're given to you on the back of your data booklet, so nothing you need to memorize, which is kind of nice. There you go. So here's an example of what these types of questions will look like. The first one's done for us, and then the second one is one we're going to do. So if we start with uranium-235, which is the stuff that likes to undergo fission, and this is kind of the most common decay equation for uranium. You don't need to memorize it, but it is just kind of a common way that uranium will break down. So we take uranium, which is so big, 92 protons in that nucleus. It's really unstable. It's like a huge nucleus. And we take a neutron and we fire it at it. And we get that neutron going the right speed, and then it goes into the nucleus of the uranium and it gets absorbed, and the uranium says, oh, I'm too unstable, and it breaks apart into two things. Now the two things it breaks into, they can be different elements, but generally speaking, krypton and barium are kind of the common ones that'll break down into. You get 3 neutrons which are produced and a bunch of energy. And these 3 neutrons are kind of the important thing that causes the reaction to continue and causes chain reaction. So that's one way that uranium can break down. The second way, or a second way, not the second way, a second way, is down below. So let's see if you guys can figure out what this missing element is here. So again, we're starting with the same thing. Neutron and uranium-235, they get smashed into one another. We get some cesium produced, we get 3 neutrons, some energy, and what is the missing element? So we're going to kind of do the math here, right? We need to have our protons and neutrons add up on either side. And the tricky part right here is this 3 in front of your neutrons. That means you actually have 3 neutrons here. So you have 3 times whatever is here. Just like when we were balancing chemical equations, we put coefficients in front of things to indicate how many of that thing there were. So in this case, we're indicating that there are 3 neutrons. So what I want you to do is take a second, see if you can do the math, figure out how many neutrons, or how much mass, I should say, goes on the top line here, how many protons go on the bottom line, and then figure out what element we're dealing with for the blank here. So I'll give you a second to do that. I'm going to break out my trusty data booklet. See if I can't figure it out for myself. And if you do get it, throw it in the chat, see how we do there. Daily, no idea, I'm confused. Okay, well that's one way. Of course, this is the first time you've ever seen this. It's kind of like the alpha, beta, gamma type questions we were dealing with before, where we had to add up the protons and neutrons on either side of the arrow and figure out what we were dealing with to begin with, what we were dealing with to end with. And you have to end up with the same number on both sides. So, is it rubidium? I don't know, Ava. I haven't gotten that far yet. Ava thinks it's rubidium. Anybody else have an answer? Want to check? See if they agree, disagree with that? Nobody else seems to be piping up. All right, let's go through it together, and we'll see if Ava is right with rubidium. So, we have this equation, and we need to figure out how many protons are on one side of the arrow, and the amount of protons needs to be the same on the other side. And then if we can figure out the mass on one side of the arrow, the mass has to be the same on the other side. So if we look at the bottom numbers to start here, and we have 0 and a 92 on my left. There we go. And over here, we have a 55 as 0. All right, so if I kind of separate everything at my arrow, how many protons do I have on the left side? So I have 0 plus 92, which gives me 92 protons. That's the bottom number, the yellow ones, on the left side of my arrow. On the right side, I have this here. I'm not sure what that is. It's just a blank. And then I have another 55 here. And then I have 0 here. So I have 92 on my reactant side, and I have something plus 55 on my product side. So what is that something? What do I have to add to 55 to get 92? Anybody have their math hat on this morning? Something plus 55 equals 92. Surely we can do this. Surely we can. 37, I don't know. 37 plus 55, let's add it together. 37 plus 55 is 80, 92. What do you know? It's 37. So this little blank down here is going to be 37. And if you recall, the number of protons tells us what element we're dealing with. So if I look on my periodic table and I find element number 37, I can see that that is indeed rubidium. So rubidium has 37 protons. So that's kind of the first half of the question, and well done, Ava, for getting that one. The second is, we need to know the mass of rubidium. We know we have different isotopes of elements. So on the periodic table, if I just take a quick look over, it says rubidium has a mass of 85.5. That is all rubidium in the entire world averaged out. This one atom we're dealing with might be different than that. So let's figure out what it is. So now I'm going to look at the top numbers here, and they're going to have to be equal on either side. So I have one neutron, or 1 and 235. So I have 1 plus 235, which totals 236 on my reactant side. Over here, on my product side, I have a blank. So I'll just draw a little blank here. And then I'm going to add to that 141. And then I'm going to add to that, and this is where it gets a little bit tricky. I have 3 of whatever's here. So that's actually a 3. So 236 is equal to something plus 141 plus 3. So if I just write it up here because I'm running out of room, 236 is equal to something plus 141 plus 3. If I simplify it a little bit further, 236 is equal to something plus 144. What is that something? The missing blank here, which goes in there. 144 plus what equals 236, or 236 minus 144? I mentioned I don't have a calculator in front of me, so to save me some math, one of you could figure out that number for me. It would be greatly appreciated. 92? Anybody agree or disagree with 92? And 144, let's see, that goes 6, 3, there we go. I like it. So this is 92 up here. So the moral of the story is the missing element, 92, rubidium, and 37. This is the blank we needed. I'm going to supersize it here. So it had a mass of 92, 37 protons, and it was Rb. Now, again, this is where some students get really confused. If you look at a periodic table, I don't think I can rotate this. Might be able to. Maybe, just maybe. Rotate. No dice. All right, let's see if I can find another periodic table. Unit 4, there it is. Here's rubidium on the periodic table. Now, rubidium on the periodic table has a mass of 85.5 and it has an atomic number of 37. This is where students sometimes get really confused because they say, well, Mr. Borden, the 37 was the same, but we have an atomic mass of 92, but on the periodic table, the atomic mass is 85.5. And the reason these can be different, ours is 92 in the example we just did, is because these are different isotopes of the same element. So the mass can change, but if you have something with 37 protons, it has to be rubidium. It can't be anything else. So when you are dealing with nuclear type equations, isotopes, don't get caught up in the mass numbers being different from those on the periodic table because you can deal with isotopes. These are elements that have the same number of protons, but they have different numbers of neutrons. That's why their mass can go up and down. All right, let's continue on with the notes. And we'll look at another example in a second of a fusion type question. So uranium-235 is the unstable isotope, and the key that is important with uranium-235 is when it breaks down, it actually produces 3 new neutrons. And that's what causes the chain reaction. That's the reason we can use uranium-235. Plutonium does the same thing, but plutonium's not a naturally occurring element. So in most fission reactions, weapons like nuclear bombs and explosions, you can take some uranium-235 and you can launch a neutron at it like that. It changes to uranium-236, and then it splits into